Hi everybody, today you're going to learn about the second fundamental theorem of calculus, or FTC part 2. So go to your notes in the next spot and you're going to want to write down everything here. Now before we talk about FTC part 2, let's do a quick recap of FTC part 1. They are related to one another, the first and second theorems. FTC part 1, there's two ways to think of it. The first way that we thought about it, this was the introductory video to it, was we took the integral of a function and we viewed this right here as being the area under a curve from A to B, two x values. And we realized that to find this exact area, we couldn't use a geometry formula, but what we could do instead is take the antiderivative, which is big F, and evaluate it at the endpoints B and A and subtract them. So that was one way of viewing it. And again, the antiderivative of f is uppercase F. Another way of viewing it, and this is more how we saw it in the accumulation packets, is instead of going from lowercase f to uppercase F, let's go from f prime to f. It's the same exact thing. You're still doing an antiderivative. We're going to do the integral of a rate. And the integral of a rate is the same as doing the antiderivative of b minus a, where f of b is the final amount or ending amount, and f of a is the initial or starting amount. And we viewed the integral of a rate as the net change. And that's really important for you to put a star around this. The integral of a rate is the net change. So you can also manipulate it, and this will be helpful for several multiple choice problems. If you want to solve for the final amount after some things have been changing, you could add f of a to each side, and the final amount is equal to your initial amount that you started with plus the integral of the rate, which will give you the net change. So all those things right there are FTC part 1. Let's jump to FTC part 2, which we led up to in the second accumulation packet. So make sure you have all this written down. Pause if necessary. So FTC part 2 is here. It mainly states that integration and differentiation are inverses of one another. And again, if they're inverses, that must mean that they undo each other. Now this problem that I rewrote here is from the second accumulation packet. So let's look at it again here. If I take the derivative of an integral from 31 to x to the fourth of f of t dt. Now, quick note, these two variables are the variables of integration. They cannot be the same as these two. They have to be different. We'll talk about that in class more, but just make a note of that. Whatever the variable you're using as your limits of integration, those variables cannot be the same as whatever is in the integrand. This is the integrand, remember. All right, so anyway, let's do the integral first, and we're going to just let the ddx derivative with respect to x hang out on the outside. The antiderivative, I'm using FTC part 1 right here to go from here to here. FTC part 1 says you take the antiderivative, which is big F, you evaluate it at the endpoints and subtract. So right here I've done FTC part 1. Now I'm going to go ahead and do the derivative with respect to F. So I'm going to do distributing the derivative of uppercase F is just regular F. And I'm going to do the derivative of the outside, don't touch the inside, times the derivative of the inside. Minus derivative of uppercase F is lowercase f here. Don't touch the inside, times derivative of the inside. Well, the derivative of the inside is a constant, so that's 0. And notice we end up with f of x again. Make sure you write this down. So we start with our function f. The derivative and the integral do cancel. We end with f, except it's evaluated at the limit of integration that has a variable. The limit of integration that doesn't have a variable, it's just a constant, that will zero out by the chain rule. So chain rule is key. Is key here. So you evaluate at the upper limit of integration if it's a variable. It could be the lower limit. We'll do one in a minute like that. And you must remember the chain rule. You multiply by the derivative of the inside. So let's actually write down the second fundamental theorem of calculus. And the second fundamental theorem of calculus, there's several ways to write it. I put two formal ones here and then a very informal one, as you can see. The two that you'll mainly see in textbooks say the derivative of an integral, and they usually have your lower limit of integration as a constant and the upper limit as a variable. That's the standard way of writing it. Of a function with f of t dt is they cancel. You're left with f evaluated at the upper limit. So you plug this in times the derivative of the upper limit. Now, it doesn't have to just be x. Like, this could be a function here, like x squared or sine of x cubed. It could be anything. So sometimes we'll see in books f of x, which just means some function with an x in it. And you have to put g here now. So a lot of notation going on here. F, g, x, and t. So you still plug in your upper limit, some function with respect to x. So it's g of f of x. And then you multiply by the derivative of this upper limit of integration. So it'd be f prime of x. These are the same exact thing. Another way that can be helpful is just a visual. Sometimes your lower limit will have the variable. Sometimes they'll both have the variable. So in that case, this visual is helpful. To do this, the derivative and the integral do cancel, and you're left with f, which is here. And first, you plug in your upper limit times the derivative of the upper limit, and then you subtract, plug in your lower limit times the derivative of the lower limit. Last year, this helped people a lot just because it's a little more visual and there's not all this notation going on. So write those down, and let's do a couple examples, and then you can practice more in class with some multiple choice. All right. So we're going to do 1 out fully without using the shortcut, which is FTC Part 2, just to prove the FTC Part 2 one more time. And then once we are totally sure that FTC Part 2 works, we're going to actually do it the quick way. So we're going to actually put a function in here. Like, instead of just having f of t or f of w, let's actually put a function, 4w plus 1. And we're going to show out the entire FTC Part 2. So that means I'm not just going to cancel and plug in the upper limit. I want to show it. So I'm going to ignore d dx for now, and I'm going to take care of the inside first. So I'm going to use FTC Part 1 here, which says to do a definite integral, you take the antiderivative, evaluate at the endpoints, and subtract. So the antiderivative of this is 4w to the second over 2. So 2w squared plus w. I'm going to evaluate at the endpoints. I'm going to plug the endpoints in, and then plug the endpoints in. And I'm left with this. So this is all FTC Part 1 in action. Now I'm going to go ahead and do the derivative of this. And I'm going to do it to the unsimplified. Like, this is not simplified at all, but I'm going to do the derivative of the unsimplified one so that I can see FTC Part 2's result easier. You could simplify it and then do the derivative, and then you'll end up with the same thing, but it's a little easier to see the result in action here. So now I'm finally going to apply d dx to this. So that means I'm going to do the derivative of this. So that means I'm going to do the derivative of the outside, which is just exponent. So I'm going to bring the 2 down, making it 4. Don't touch the inside, x cubed to the first, times the derivative of the inside. And then what I'm going to do is the derivative of x cubed, which is where I'm getting a 3x squared. And then what I'm going to do is the derivative of this. Now, this is all just a constant. It's a number. So it's 0. So I'm just going to leave it like it as a 0. What I'm going to do next is rewrite it as 4x cubed times 3x squared plus 3x squared. Notice I have a 3x squared in this term and this term, so let's factor it out right here. I'm left with 4x cubed plus 1. So now I can see this result really nicely. This and this are pretty much the same exact thing, except I've plugged in my upper limit of integration for the variable. That's how I get 4x cubed plus 1. Then I multiply by the derivative of the upper limit, which is 3x squared. So again, it works, and it's the same as just plugging in the upper limit of integration and applying the chain rule. All right, so let's actually do the short way, because this is how you're going to do it on the AP exam, now that we're fully sure that it works. Here's the first example. And for the first example, let's take the derivative of the integral from 3x to the 4th up to 7. Now notice this one's different because the lower limit has the variable. The upper limit is the constant. So I'm going to do the shortcut. And here is the visual definition. You're going to plug in the upper limit, plug in the lower limit, subtract, apply chain rule. So first I'm going to plug in the upper limit, which is right here, times the derivative of the upper limit. 0, he's gone. Then I'm going to plug in the lower limit to my t, which is right here, and multiply by the derivative of the lower limit. So then I'm just left with a negative in the end, because the first one was 0, not the second one. And last example, I'm going to have, again, my lower limit be the variable one, except this time instead of just having a function, I'm going to have an actual function written out here. So I'm going to plug in my upper limit here and here. You have to plug it into both variables. So that would be here and here, times the derivative, which is 0. So this whole thing is 0. Then I'm going to plug in my lower limit to both variables, which is how I get this, times the derivative of the lower limit. That is not 0, obviously. So I have negative of this expression with the lower limit plugged in times the derivative of the lower limit. That's the chain rule in action. All right, so make sure you have those examples written down neatly and fully. We will practice in class. I will see you tomorrow.